Welcome to today's webinar titled Improve Performance and Reduce Failures of Centralizers. Second in the webinar series of MSC Solutions focused on oil and gas industry. My name is Srinivas Reddy and I am Product and Industry Marketing Manager at MSC. With me today is Juan Lopez de Alda, who is a Senior Application Engineer in our support team, and he comes with broad experience in motion dynamics and mechanism problems across several industries. And over the past few years, he has been focusing on helping our oil and gas industry customers with their systems and controls analysis. For the benefit of those who are new to MSC Software, I would like to take a couple of minutes to introduce our company. MSC Software is the leading global provider of virtual product development tools, including simulation software and engineering services. We have been helping companies reduce product development costs and increase product innovation for over 45 years. And we provide a broad range of tools and applications and services that help companies to virtually develop and test their products. Another core competency is the engineering process improvement that we will touch upon briefly at the end of this webinar. Our VPD tools are all available as an integrated solution set offered through flexible licensing systems, giving you a range of options and the convenience of accessing MSC's entire simulation portfolio. MSC's simulation solutions also have a broad list of applications in the oil and gas industry. Here is a set of key segments our product and solutions are used for. Seals play a critical role in safety and operation of oil and gas wells. So our products are used for nonlinear analysis of a large variety of seals used in this industry, including packet seals and blowout preventers, and which was the topic of our last webinar. Other applications include bottom hole assemblies, including drill bit simulation and design, which involves contact and wear and tear studies. Offshore structural analysis, accounting for fluid loads and dynamic behavior, and then the storage and pipeline structures can be designed and virtually tested for both static and dynamic response, which could involve blast simulation for safety and security. The control systems, they are integral to oil and gas production, and MSC offers solutions that can, in addition to simulating just the control systems, also include coupling with the mechanical systems and even possibly structural deformation response. And the turbo machinery used for power generation and compressors in gas production, they have both safety and operational performance design requirements that can be addressed through the MSC solutions. Finally, the pipeline devices, they're those that are generally passed through pipes or wells to serve several purposes, which include maintenance and transport of various tools, analysis of their stability, the motion, dynamics, and any kind of failure is critical for their efficient performance. And MSC's integrated solution set is ideal for these type of systems. With that brief introduction to MSC and its solutions relevant to oil and gas industry, let us now move on to the central topic of this webcast. After a brief review of centralizers and challenges in the product development, we will review the simulation solution offered by MSC and followed by a specific example. And at the end of this session, we will have a Q&A to address any questions you may have on today's presentation. At this point, I would like to turn over the control to Juan, who has very great experience in analyzing centralizer systems. Juan, please take over.
Thank you, Srinivas. Welcome. Let's start with a brief review of centralizers and their uses in the oil and gas industry. Centralizers are normally used to keep tools and pipes centered in the well or casing, and as they pass through them, as they carry tools with them. Most of the centralizers are rigid components placed on the outside of tools or pipe components. Some centralizers need to collapse or expand as they go into narrowings or expansions of pipes or wells. The design of the centralizer mechanism as it collapses or expands must consider important physical considerations such as friction forces, exterior fluid forces, temperature changes, mechanism dynamics, fatigue of components and life, etc. Centralizers are submitted to a severe dynamic interactions with the surroundings that they depend on the arrangement of the pipes and tools in the overall assembly that needs to go in and out of the pipe or the well. Those severe forces that are these components withstanding, combined with the forces along the other assembly components, could produce serious operating problems and difficulties, such that the centralizers could get stuck when they are getting in or out. The centralizer components could deform beyond the expected values of their estimated deformation, or they could break apart, breaking the whole mechanism. The centralizer mechanism will adapt to this tubular surrounding in such a way that the forces it needs to withstand must be a minimum, have a minimum value. And by doing that, it will allow the assembly of tools to perform better under these circumstances. So, as we see, there are many challenges that the centralizers face, and we are going to mention some of those. The designers of the centralizers, when they are designing it, need to take into account several things. The centralizers face a very abrasive environment that could affect their function and performance over time. The centralizers are exposed to corrosive fluids in the field that could affect the performance. The continuous motion and contact with the pipes and wells could lead to friction, wear, and tear. The changes in the pipe diameters and orientations would also mean that the centralizer could experience large deformations, leading to high stresses and strains. The centralizers should be able to navigate sharp corners as well without jeopardizing the life of any of its components. Workers should be able to insert and extract a centralizer with the same effort, going in or going out, especially considering the possibility that the pipes might not be concentric. So the design should experience symmetric force distribution as much as possible during the insertion and extraction. Another important aspect is the ability to get unstuck if it happens. A centralizer that is stuck in a pipeline can lead to additional operational expenses. With so many field conditions to account for, designers would have to study a gamut of geometries, mechanisms, and materials, and analyze various configurations to come up with a design that can provide an optimum operational performance. So let's talk a little bit about how the centralizers are classified. There are different ways to classify centralizers, and we are only going to mention a few. One of the ways that can be classified as the way that they are driven. How do you drive this mechanism? There are centralizers that use screw mechanisms. There are centralizers that use hydraulic actuators. There are centralizers that are spring-based. And there are other options that we are not mentioning here. We are focusing this presentation on these driven type centralizer mechanisms. Others are not driven, are static, the rigid ones, but we are going to focus on the ones that are driven. A screw mechanism, for example, can be used to control the opening and close of the central part of the centralizer mechanism. And by doing that, force the bows to curve or bend. The screw can be actuated with hydraulic forces. Hydraulic forces can be applied directly to a central part of the mechanism to control the opening and closing of them, and the bows will curve or bend accordingly. We're going to see some of these central parts in next slides. Internal springs, different than the bow springs, can be used to move the central parts to make the bow spring expand to the surrounding diameters. The springs are harder to manipulate to actuate the central parts. Opening and closing arms is another way of driving the centralizing mechanism. Those arms can open the central parts also to the open position and expand the bows by doing that. This is the kind of mechanism that we are going to review in this presentation. Other possible configurations and design can be obtained and modeled, but in this case we are only focused on this arm opening and closing arms driven centralizer mechanism. Basic components and considerations that a centralizer, a designer, needs to account for during the designing of the centralizer mechanism are the actuation system. How is the actuation or the driving part of the centralizer? How can we control how to open and close the bows when needed? What are the materials and dimensions of the flexible bows as they going to be withstanding this severe abrasive environment? The internal guiding mechanism, what is it made of? Screws, springs, opening and closing arms, etc. The central parts, the parts that will be in contact with the pipe and casing, what properties do they need to withstand this friction and impacts? The dimensions of the body components that hold the internal guiding mechanism at the center and hold the bows at the end. And the parts that are similar to any of those centralizer mechanisms. This is a picture, as is shown in this slide, of one of the centralizers, the ones that we are going to show in this presentation. And in this picture, you can see the components. You can see the flexible bows. You can see the central parts are in yellow. And you can see the interior mechanism. We'll see more of them in future slides. A successful design needs to address several aspects of the centralizer performance. Let's go through a few of them. The actuation of the mechanism should be easy. It should be easy to get in and out of the pipe or the well, while it could be automatic or driven. The springs that keep the bows open need to be as soft as possible, such that the normal forces due to the contact between the central parts of the pipe are minimum. As the mechanism navigates through the pipes, the expansion or retraction of the system should be smooth and avoid sudden motions. When it comes to bows, they should flex only in bending as possible. Guides of the mechanism should be designed to prevent other deformation modes like torsion. Since friction and damping play a critical role in the system performance, they need to be controlled mainly at the center of the mechanism so that the loads get distributed as evenly as possible. There are a few other factors taken into account for all designers. The symmetry of the system is maintained so it behaves the same way during insertion and retraction. The mechanism is also made of sets of diametrically opposed bows on arms, and with the possibility of having as multiples of these opposing blade sets as required. The picture shown in this slide is showing a centralizer mechanism that has 4 sets of opposing bows. And as you add more sets, the dimensions of the bows would change. All these challenges can be studied and understood via simulation. As you saw, the challenges are not easy, not simple, plenty. So simulation is a good tool to study all of them, with the following benefits: time and cost savings due to quicker and cheaper design iterations, designs that can be studied earlier in the development cycle and reduced number of prototypes that need to be built and validated, safer than working and testing on the field or the lab, so the number of tests will be reduced and the exposure to harsh environment will be minimum. Many more design variations can be studied and in less time, and they can be compared to each other to see the benefits of one with respect to the other. What-if studies. Very hard to replicate field conditions can be simulated to understand the behavior of the centralizer under these circumstances. There is a lot of benefits by doing simulation. There is a big advantage of doing it in simulation during the design cycle, and they clearly indicate big savings in time and money for the companies that design them. This slide shows the simulation process that can be followed to do a design and analysis of a centralizer mechanism. The first step is to account for the flexibility of the bows. So you generate flexible bows inside an FEA software. Validate the model of those bows such that you have a believable model content of these bows once they are passing to the motion world. Do an optimization of the opening mechanism to determine the spring parameters and preloads that require to minimize the normal forces when the centralizer is in the open position. Those parameters that can be used for this optimization could be the spring stiffness and preload, an actuator force parameter. There are two possible ways to run then the dynamic analysis of the mechanism going into the pipe. So first we start with the mechanism getting into a narrowing into a pipe. We move the mechanism and hold the pipe fixed into the ground, or we fix the mechanism and move the pipe going on top of the mechanism. In this case, we follow the second one. We move the mechanism and hold the pipe fixed to the ground. I meant the first one, I'm sorry. Since the intent of this model is to later attach it, decentralize the mechanism attached to a couple of tools, one in each side, and move it through these narrowings, we decided to hold the pipe fixed and move the mechanism going in and out. The fourth step in the simulation process is to change direction. Once it has gone in, we want it to go out. So we want to change direction during the dynamic simulation and see how it behaves when it's going down. The next step in the simulation is to gather all the data that we can and we need during this analysis and compare to measured data or calculated data that it can give us credibility on our model. The next step is to then go and measure specific data for our particular discipline. In this case, we were approaching this analysis on a fatigue disciplines. We wanted to understand the life and cycles of this mechanism. So our objective was to measure the life and fatigue and cycles of these bow springs. So we measure hot points and stress values at in all the flexible bows. And we then conduct the fatigue analysis. Now we are going to go in detail into one of the models. The example that we are going to present here is of a centralizer that was trying to account for all the indicated considerations and meet all the challenges presented by this problem. The centralizer model will include different components and different pipe configurations. It will include an actuation system that will allow the bows to initially expand. It will include a general mechanism that drives the bow to move gradually to conform the different pipe diameters. It will include flexible bows that will deform and stress as they change shape. It will have all the contact forces between pair of components that might touch bows and pipes, etc. And it also will include a release mechanism that will eliminate the possibility of the centralizer getting stuck when it's going in or out of the pipe. Also, the mechanism model by MSC will include full parameterization to do design studies, design of experiments, and optimization. All the measurements required to validate the initial model to get and predict motion characteristics, stress, frequency, content. It will also have defined the design objectives and measurements required for all these design of experiments and optimization, and the possibility to compare data measuring the field to what the model is giving us. The completed study follows a sequence of analysis that completes this fatigue discipline. Because this model could be used for a fatigue discipline or a vibration discipline, but we decided to do a fatigue study with it. And what this study includes is reading a CAD geometry. In this case, it was done with a parasolid geometry, building the parameterized mechanism inside MD Adams, generate the actuation system using EC5, that was one option we had, or doing the actuation inside MD Adams. If the actuation system needs to be studied in detail, the model of the actuation should be done in EC5 and run simultaneously with MD Adams. A simplified way to model the actuation was a force containing the forcing function of the actuator together with the spring force. And this was done as one single component in this study. Then we need to also generate the flexible bows using Patron and MD Nastran, 1/8 of the bow and 1/4 of the bow. So we split the bows in 8ths and quarters, and we'll tell you very soon why. And then we assemble the complete system in MD Adams. We generate the internal arms guiding mechanism, and we put the actuation, we put the bows, and we assemble the model and do the design studies, design of experiments, optimization, and for that we use MD Adams Insight. We did also a validation of the model by reproducing the mechanism getting stuck in one position, by measuring stresses and loads at certain points of the simulation and compare it to the field measurements. And after that was done and the model was valid, we calculated life and cycles of the bows. So let's look at the different parts of different components that were used to model this mechanism. The pipe geometries that we used. We had to use a very high degree of precision for the contact forces between the different components and the pipes, with the purpose to minimize the noise that is produced during those contact forces. And the noise would be generated by the imprecision of the geometry. If the more precise, the more accurate the geometry is, the more smooth, the better the contact forces would be. The pipes were done inside CATIA, and they were made of steel, regular steel. Different pipe diameters were tested at some point. Different narrowing ratios were tested. All of the analyses were done going into the narrowing first, and then into an expansion, and then coming back. It is possible to do analysis with different sequence of narrowings and go gradually from one narrowing to another. Is it also possible with this model to do analysis with narrowings that are off-center? The analysis that we did were done moving the pipe while the mechanism doesn't move longitudinal. This was done initially to test the mechanism, and later the pipe was fixed and we moved the mechanism inside and out. The speed that the mechanism moves in and out of the pipe was a design variable, but no real studies were conducted to determine the effect of different speed having the resulting stresses on the bows. Let us now look at each of the aspects of the model identified in greater detail, the mechanism itself. The actuation shown in this part of the model has been simplified to a component force. That was enough for this model. We concluded that we didn't need to have a complete model of the actuator, and we were not interested in the dynamics of the actuation, but in the response of it. So we were able to capture the response into a single component force. So it accounts for that together with the spring force that it has. And the actuator, what it does, it holds the spring close when required, and it can close the spring, the bows, or the whole mechanism as needed. There was a small optimization analysis done in this area to, as I mentioned previously, to minimize the resulting contact forces between the central parts of the actuator and the pipe when it opens, in such a way that the mechanism opens initially and barely touches the walls of the pipe with not much force. The spring load, the spring preload, and stiffness were used as variables for this optimization, and we came up with some values to get, when the mechanism gets open, to have some contact normal force, not to be lower than a minimum, but as minimum as possible. The objective function for that optimization was that normal force, and it worked relatively well. It was a fast simulation to obtain these parameters, the optimum values of these parameters. Now let's focus in the internal mechanism, the guiding mechanism. The main goal of this internal mechanism is to guide or allow easy opening and closing of the external bows. A series of cam follower arms make the opening and closing of the bows gradual and smooth, and the fact that it's completely symmetrical along the length of the mechanism makes the front of the mechanism behave the same as the back of the mechanism when there are no disturbances. So I can move the central mechanism in any direction of the pipe and I will get the same reaction. The interaction between the cam and followers is modeled using contact capability. The arm that slides inside the cams also include contact forces that act as stops for the arms and facilitate the opening of the arms. The central parts, in yellow, those are the frictional parts, have the information to rigidly attach the flexible bows. The flexible bows will attach to those parts in one of their ends. The central mechanism, whose geometry is shown in the picture, the central parts, with the color yellow, the geometry was completely modeled in Adams. We didn't import anything from CAD because of its simplicity in the geometry. The guiding mechanism also has a couple of stops, one in each side, model as small increases of diameter in the center rod. That will limit the length of motion along the center rod of the opening during the opening and closing of the mechanism. The distance between those two stops, the front and rear, was also a design variable. The stops were parameterized, and the separation between them was controlled by the designer. The flexible bows are the next part of the mechanism. They were created using Patran and MD-Nastran. The bows are meshed in Patran, and the model analysis is carried out using MD-Nastran. During the analysis, a model neutral file, .mnf file, was extracted for each bow component of the complete bow. This file contains all the data necessary to model the flexible component inside MD Adams. Then we imported this MNF file into MD Adams and positioned these bows components or bows parts into the corresponding location to form one complete bow as it's shown in the upper image of the slide. You can see there that there are, not so clearly, but you can see that initially there is 1/4 of the bow, another quarter, and then it comes two small pieces of eighths of the bow put together. Different analyses were executed during this study to determine the validity of these bows and to determine the linear range, what would be the linear range during these exercises. And we had to then create two MNF files, one for the eighth of the bow and one for the quarters of the bow, and then put them all together. The same bow, all the bows that you see in the lower image use the same MNF. Those two MNFs that were generated will be used for every single flexible bow. And the MNF files contain all the model stress and strain vectors that will be used to calculate the stresses and strain during the analysis within MD Adams. There are several contacting components is one of the important points of this modeling. The contacts, there are plenty, several parts touch each other and need to be defined correctly. Modeling of these contacts between these components require a relatively good precision to validate the model and to come up with good stress and strain information or vibration content. The picture shows some of the ones that are mentioned. They are shown as arrows in Adams. I didn't put the numerical values, but I am able in Adams to show each contact with an arrow force. The most important forces are the ones between the central parts in the yellow color and the pipes. Also between the bows and the pipes, the bows and cams, because as the bow flexes, the cams have the green color, and the bows, as the bow flexes, is going to touch the cams. And also all the stops that the mechanism has. The contacts were all modeled as simple functions, impact functions, standard impact functions inside Adams. The parameters of the contact forces were defined based on geometry and material properties. Some of the parameters, such as damping, were modeled as design variables, and design studies were executed to determine values that would suit this analysis. So basically, I was not able to come up with values, and I put design variables to come up with the most appropriate value for the simulation. There are different pipe diameters that we have to go in and out. There is no standard procedure of how to test it and how many of them should we go in and out. So I choose different ones, and I wanted the mechanism to be able to go in and out through different diameters. But I also wanted the mechanism to reproduce when it gets stuck. So as it's coming in or out, it might be a case close to the one that is shown in the image where the bending of the bow is extreme and the mechanism can get stuck. Basically, the summation of the forces does not allow, and there is not enough resulting forces to pull the mechanism in one direction. So there is a release mechanism that was put in there, and it's not shown in the graphics. It's a concept design, and it's still in development, so I don't want to show it yet until it's complete and is validated. It's done his job for this analysis. I'm able to release the mechanism once it gets stuck. And it was done initially with a crash-worthiness type of mechanism that is being used in the automotive industry. So when the force exceeds certain value, something gives and allows it to bend beyond the point that it was bending. In this particular model, what we did is we put a force that models that effect of allowing, of giving some compliance and allow it to move beyond the point where you get stuck. Some optimization was done to obtain the best possible combination of the parameters that were used in that force. I'm sorry I cannot show you the release mechanism, but is a tool, is something that is in concept and it can work pretty well later on. So those were the main components of the model. Now, besides having the model built and tested individual components and make sure that each of them are doing what we expect, we put parameterization in the model. We wanted to understand how the model is going to behave beyond certain parameters, beyond certain values in the parameters. So we can do studies, different studies, determining the effect of the most important design variables for the designer, and so they can focus on that particular area and optimize their design. Some of the parameters used in the model were speed, length of the internal mechanism, pipe diameters, cam separation, length of each bow, follow diameters, some slide opening where the arms slide as is shown in picture. That picture shows a little bit of this opening inside the cam that allows the arms to move. Actuator force parameters, spring parameters, friction force parameters, and a few others. We only took some of these variables and did in DOE studies. We didn't do it with all of them. So we didn't either complete a full optimization, but it's set up to be run with Adams Insight and do a full optimization. The complete setup, the complete system can be easily set up or prepared to run a simplified optimization. Many variables can be considered for a comprehensive optimization. Not all of them were used in these studies. Geometric variables have been included. This is because the geometry was all generated. Most of it was generated in Adams, and that geometry is the one that has parameters that can be changed. If you have geometry developed in the CAD environment, then the parameterization follows a different path. There were also functional variables that can be included in the studies, and the goals for these optimization and design studies, were to minimize the spring loads, the actuator loads, the normal forces between the central part and the contacting pipes, and to minimize the stress forces, stress concentration on the bows. We didn't focus much in the frictional part of it. After we had all the parameterization and the mechanism ready for all these studies, all we had to make sure is that we had the correct measurements. What do we need to measure so the designer can evaluate their design or the studies? Displacement, velocities, accelerations, were used to verify the model, that the model was running correctly. Loads and reaction loads were used to study to determine that the way the system was modeled was correct. And the model also then included all the measurements for the stress and strain information of the different flexible components, in this case the bows, all the loads for the other components. In the movie that you are seeing, you can see that I'm only running a little bit of the analysis on the most critical part of it, well, it's getting the higher stresses at some node in one of the bows. And once the model stresses and strain vector were included in Adams' durability was used to calculate at every iteration the stresses and deformations and prepare all this information into a particular files, the setup of files for the fatigue and life studies. So I have, as a result also of my run in Adams, all the files that now can be used in a fatigue software to calculate life and cycles. And then, once I have all the measurements ready, all I have to do is evaluate the results, determine that my model is running as I want it, and that I can get it on stock, that is validated, and it produces believable results that I can use to predict changes in the design. We use also an FEA nonlinear analysis using MARC, MSC MARC, or MD Nastra and nonlinear, to calculate the stresses on the bows and compare it to what is the difference between using this linear approach in Adams and the nonlinear in MARC. So what we did is we enter into the MARC model of the flexible bow, we enter the boundary conditions similar to the ones that we have in our model. So we move one end of the bow as if it was opening or closing, and we put the contact forces with the pipes as it was moving into or outside or out of the bow, and compare the values to also come up with a good understanding of our modeling approach. Another way was to try to get it stuck, make an analysis purposely to get it stuck, and try to match physical tests. I'm showing a couple of other movies to see what you can do within the post-processing in Adams. Within the post-processing, I can set up cameras inside the mechanism to see different things as they are moving in and out of the pipe that I cannot see in reality, I cannot see in the physical mechanism. I'm able to also generate traces of the motion of the different parts, calculate clearances and how close they get parts to each other, and prepare whatever presentation that I need to do to show this exercise. Also, in the other movie, I can see the dynamics of the full exercise. How does it initially move in and out? How does it open? And then the initial motion in and out, that it has its own dynamics. The lower movie shows a complete cycle for one narrowing, shows the motion of the mechanism, opening, advancing, and returning back to the original position. Okay, I have one more movie that I wanted to show you, just with the purpose to show you that I can follow the mechanism in different ways, and I can study in different ways. In this case, what I was trying to see is changing the view of rotation of my camera as the mechanism is going through the pipe. Like if I would have had a camera perpendicular to the pipe inside the ground in the well and see the mechanism passing by, and I see it coming, and then I see it in the front, and I see it passing by. With the purpose also to see the effects. In this case, I wanted to see the effects or the changes if I do change the speed of motion of the mechanism. So with that, I want to tell that it is a complete study. As a summary, it's a complete study. It's a fatigue discipline study that includes flexible components, includes optimization, includes motion studies, and it has the way to provide all the files for the fatigue and life calculations. So let me pass now the control back to Srinivas. Thanks for your attention. Srinivas?
Yes. Thank you very much, Juan. You have seen how MSC solutions are used to solve this complex problem, accounting for controls, flexibility, and motion of centralizer mechanisms. Let me now take a few minutes to discuss how you can enhance the value of the simulation tools and increase your engineering productivity. Using simulation often creates a lot of valuable data. Simulation data can be any type of data that is relevant to your analysis and your simulation. It could be all your models, model configurations, CAD/CAM files, any kind of CAE files, simulation results, or requirement documents, or material properties. And it could even be your non-CAE type files, such as Word documents or Excel spreadsheets, or any other type of template or automation files, or any other content that is generated by you. If these massive amounts and various types of simulation data, if they're not managed effectively, it could result in poor reuse and knowledge sharing, in addition to communication and process inefficiencies within the company. So the real challenge is to get the simulation work done better, faster, and cheaper, and be able to run more and more simulations and improve the credibility of this analysis by having a complete audit trail, linking the results back to your design alternatives that have been analyzed. Sim Manager from MSC Software offers the possibility for everyone to collaborate and get their simulation work done better, faster, and more reliably. It is a web-centric framework for sharing and collaborating and controlling your simulation data and processes. It represents software infrastructure that will securely store, protect, and tie together all of your simulation activity. It is built using a service-oriented architecture, which makes it easily extensible and customizable to meet your needs. And through this web-based platform, your simulation data will be securely available around the globe 24/7, version controlled, and with secure role-based access control. One last point before we get to the end. In addition to providing the simulation software, data, and process management solutions, MSC also has a large services team placed across the world to assist our customers to quickly analyze and realize and enhance the value of their investments. And by executing simulations and training your employees, automating processes, or implementing web-based systems to manage and coordinate simulation data, they can engage on many different levels. With that, let me summarize what we have covered in this webcast. Using MSC's simulation solutions, we have demonstrated how to analyze a complex system such as a centralizer. In doing so, we demonstrated how various nonlinearities are accounted for, including the large deformations and how the contact interactions, and also the handling of instabilities like getting stuck. By integrating controls, mechanical dynamics, and FEA used for flexibility, so we could obtain an accurate solution which reduces physical prototypes and improves the fidelity of the simulation. We have also explained how MSC can provide simulation data and process management that can help improve your productivity. In summary, MSC solutions come with the advantages of providing accurate and robust solutions within a complete simulation framework, including your process management. Once again, thank you very much for attending this webcast, and please stay online for Q&A session.